The next tabular foundation model we're going to look at is based on LLMs. Okay, the LLMs that we are familiar with from our everyday life. Our focus is going to be not on in-context learning as we did for Tab BFM, but rather on few shot. Okay, basically we retrain the model using a small number of examples. Okay, now we can imagine that if you have an LLM with modern capabilities, then it can do a non-trivial prediction even in a zero-shot manner. Okay, you have your row with your attributes in it, and you have a description of your task, and you ask it what is this attribute, which can be Boolean, yes, no, or some regression task. And you can imagine that it does better and sometimes much better than a random guess. Okay. The focus of top LLM is on the question of how can you improve the LLM if you have a few shots, okay? If you have a few examples, how do you produce a better LLM, okay, for the future use? Okay, now this approach I mentioned that it has also been applied to full relational databases recently, and the main focus of the Tab LLM paper is basically on how to describe the tabular data to the LLM, how to write it in a way that is textual, natural language, in a way that maximizes its ability to use its powers to make the right predictions. Okay, so our input setup is quite similar to what we've seen for a TAPFN. We have a small set of examples, okay, tuples and labels, values that we want to predict. So these are the examples. And then we have a new input, tn plus 1, and we want to produce the output yn plus 1. This is our setup. Okay. Now, if I give you an LLM, you have several ways of using the LLM for this task. One is in context learning. You prompt the context D and the question T n plus 1. Okay, I'll say that if you also have a description of your task, then you can also prompt that one. Okay, you can say, well, this is a machine learning model. It is designed for some things, yes, but we can fine-tune this model from from the beginning, or using all of the parameters for my new task using my few examples. Well, that's heavy. That's a lot of work. You have a lot of parameters there, and it's also not clear how your few examples, and we're talking about tens of examples, how they're going to really affect the LLM. But there's also a third approach, which is to fine tune not the full LLM, but a tiny portion of the parameters for the task at hand. Okay, and this is called parameter efficient fine tuning. We'll see that. Okay, now TabLLM proposes to use one for black boxes and three for an open source model, but three also have the advantage that once you train it, you can use it with other sources or provided to other repositories to use without providing the few examples. So they focus really on what you can do with an open source model. Okay, so parameter efficient tuning. Here is the technical idea. So remember the concept of attention. You have queries multiplied by the keys. Okay, some normalization. On top of that, we apply softmax. we get a list of weights and an weighted average over the values. Okay. Here in PEFT, the idea is to use a small set of additional variables. Okay. We introduce this number of or this vector of parameters in the length of the keys. Okay, so it is element-wise product. So WK element-wise product K, and another vector of parameters, weights, element-wise again on the values. Okay, so we have this small number of new parameters that are essentially new weights on the keys and the values. Okay. They also add these some parameters to each FFN. Okay, so the FFN is not, if you start with something like an activation over some linear layer, then they multiply it again with some vector of weights for the feed forward. Okay, so basically we have three vectors of new parameters for each layer. Okay, so the total number of parameters that we were adding to the system is L, the number of layers in your LLM, times, and then the sum of these small data independent dimensions. Okay, so in principle, this is a small number of parameters. And now the main focus of the paper is basically on how do you serialize your examples X, Y, or TY into textual prompt. And they look at different ways, like a direct list, XI, YI, or TI, YI, sentence per cell. The column name of something is this value, or the column name of our instance is value. We'll see some examples in the next slide. Or use actually an LLM like a GPT to transform the sequence of tuples of examples into a sentence. Here's an example of a person who is this and that and that. Again, we see an example for that. And also use an LLM that is fine-tuned to table to text. So basically, you can provide it with direct tabular data. And this is an LLM that they took from Hugging Face. Okay, so here's an example. A list of attributes, then you just write down the different cells. Age is 69, type of job is retired. Just write it down, this technical uniform syntax per cell. Using an LLM, you can actually transform it into a sentence. This person is 69 years old, comma, retired, comma, single, and so on. So this is actually a human readable paragraph out of the row. Okay? And combining everything together, this is basically their approach. So you start with tabular data with K labeled rows. Okay, these are your few shots. Now you serialize your each tuple or your table basically into text. Each row gives you a chunk of text. This can be, well, they talk about some manual template that they provided or table to text mechanism or an LLM. Okay, that they use for this task, and they have as I said, a sequence of such serializers. Okay, so this is the second step. You're producing textual content from your table. The next step is basically you are using your examples. Okay, and each here has a, it's a value. Okay, you use these examples that you have in order to go to your few parameters that you've added, okay, and apply learning, backpropagation. You have the sentence, LLM, you have the predictions, you have the labels. Based on those, you apply backpropagation, and that's how you train, you fine tune your model. Okay. And then you use your LLM or your new LLM, your fine-tuned LLM for your task. Well, here is my row, and I don't know what the income is. Okay, so I describe here the content of this row, and I'm asking, does this person earn more than 50K? And here we also assume that we have a description of the task, and we also um, say that this task is a Boolean, yes or no. Okay, and that's it. From that we get we feed that as a prompt to the LLM and get an answer out of that. So this is the idea. Very simple, but illustrates a few concepts. So several things that we've been using, uh, which LLM they were using, what technique or library they were using for the fine tuning, and an example of their fine tuning time for 64 examples is 3 minutes. Okay, so you see that it does take some time. But again, after you apply this few shot, you have your new model that you can use and improve the results. And inference time is 10 milliseconds for example. So inference, after you applied your fine tuning, is actually fast. Okay, and they try out different examples, different alternatives, different baselines. This is Tab LLM. Okay, and you see basically that with zero examples, that's basically zero shot. But since they use an LLM, it gives you a non-trivial performance. Not trivial performance would be 50% because this is a AUC, okay, area under the curve. But with zero examples, they already are at 65%, which is also GPT with no examples or with one uh, example, okay, and a description, of course. Okay, and then they show basically as more examples you provide, they try out different models. Some models are really not designed for a few shots, but we see that Tab PFN with very few shots starts doing something reasonable. And the more examples you add, and really a small number of examples, the better Tab PFN gets until at some point it surpasses uh, or a Tab LLM. Okay, and other models also surpass it by according to this experiment. So their case is basically that if you have very few examples, then a Tab LLM is a better approach. These basically use a collection of 9 public data sets. So in that respect, this is a thorough experiment.